of linear regression, we're going to be continuing to practice the process of using data to work backward to come up with an equation to represent the, to model that scenario. So there is one new term, there's one typo on here. I don't know why it's on here twice, but number 1 here, this data set has A and B is listed twice. Okay, so we're just going to mark out that second B. You want to mark that out with me? I'm actually going to wipe mine out. You can just mark it out. I don't know why that got printed on there twice. My bad. Okay, but what we're going to look at here, this on the front, we are just practicing the process. Okay, the process of linear regression in Desmos. Now it says in these instructions to find the linear equation that models each data set, round all decimals to the nearest thousandths. So that's a little different than yesterday. So we're rounding to the nearest thousandths. And to identify the coefficient of determination. That right there is a new term. The coefficient of determination, okay, or R squared, okay? What that is, that's one of the statistics that comes up on Desmos when it shows us what M equals and what B equals. It also shows us an R and an R squared value. Okay, so we're going to talk about what that means today as well. So I'm actually going to use that space where that typo was, where we marked that out, this empty space here. I'm going to use this to write out what that is. What is the coefficient of determination? Okay, so kind of here in just this blank space, I'm gonna type so it's a little neater than my handwriting. Okay, so 2 things. First, I guess I'll just do the definition. Okay, so the coefficient, oh, well, gotta be in there now, okay, of determination for R squared. I don't know if I can type the R squared. I'll write that into the side. Okay, but the coefficient of determination is the value which measures how well the regression model. Now, when we say regression model, the regression model is the equation that we're coming up with. So how well the equation, okay, fits the data. Okay. This value is between 0 and 1. And the better or the closer the value is to 1, the better fit, thus the better predictability. And I'll make that bigger here. So that's that definition that we want. Okay, so coefficient of determination again, that's your R squared. So when we put our data into the calculator and we get our statistics that pop up after we do the regression steps, okay, there's going to be an R value and an R squared value. So I'm going to show you that with this first data set, and we're going to look and identify what that R squared is and kind of talk about what it means for this data set. Is everybody good with that definition? It's always going to be a value between 0 and 1, and the closer to 1, the better. Okay. That means we can make more accurate predictions. The better predictions come from an equation when r squared is closer to 1. All right, so I'm going to split screen here with Desmos and enter my data. So remember, this is the process we learned yesterday. So let's refresh. You're going to hit the plus table, okay, and we're going to enter our data. Okay, so carefully enter your data and make sure you're not having any typos or mistakes or anything, because that'll throw everything off if just one of your numbers is wrong. So we got our X column values. Now our Y values are going to be here. Okay, so I've got my data. Who remembers what I do next? Once I have the data entered, what is the regressions process? What do I type here? Uh-huh. Exactly. It's right there up on the board in marker. Okay, but remember, it's the y equals mx plus b form, but we don't use an equal sign. We use the little tilde, the little squiggle. Okay, and when we type the y and the x, the variables, they have to have that 1 after them. The note outlines back here on the purple table if you want to grab one. So that's going to be y1 tilde mx1 plus b. So when we do that, it knows we're looking for regression, and it automatically comes up with these statistics and parameters. Okay, so I have all of this information. Yesterday, we were just looking at M and B and writing our equation, which we're still going to do that today. We're going to come over here and we're going to identify M and B and write our equation. But this time, I'm also going to identify R squared. So my R squared is 0.0. It says to round everything to the thousandths. That's 3 places after the decimal. So 0.98. Okay, is that very close to 1? It's 0.09. It's not 0.9, it's 0.09. So that's not even 0.1. Okay, so it's definitely much closer to 0 than to 1, isn't it? Okay, so this is not a great fit. We're going to write the equation, we're going to answer the question, but just know our prediction that we're going to make using this equation we write, it's not going to be a great prediction. It may not be very accurate, okay, because this coefficient of determination, it determines whether it's a good fit, whether you'll make a strong prediction or not. So this one is not going to be a great fit. If you want to make a note of that, not a strong fit. So not great predictability. Now we're still going to do this just to practice the process. So my equation, my M is 9.535 if I'm rounding to hundredths. Okay, so make sure you round this correctly. Remember, thousandths is 3 places, but you look at the next one, that 9, it's going to round that 4 up to a 5. So that's my M. I've got X plus, and then my B is 66 point, and then rounded, that would be 379. So that's my regression equation, okay? But my R squared being close to 0 tells me that this equation is not a great fit for this data, okay? Now I'm going to go ahead and use it to make my prediction. They want us to predict when X is 15. So we're going to plug that in there. So 9, oops, started to write 3. 9.535 times 15, 66.379. Okay, so I'm going to come back over here to my next line and I'm going to type that in. So my prediction is 209.404. Now I'm not confident that that's a great prediction because my R squared was so low. Now let me show you graphically what that looks like. When you're R squared, that coefficient of determination shows not a strong fit. This full screen real fast. Okay, so let me zoom out because those numbers from our table were here. So you can see the scatter plot that it created with the data points. And then look at this line of best fit that it created with our linear regression. That doesn't go through many of those points, does it? That does not look like a great fit. So we can see a visual of what a low R squared value looks like. It is not a very good fit. That line of best fit, not great. Okay, it's not a strong correlation. Does that make sense? All right, let's try the next data set. Okay, so the next data set in number 2, I'm going to add table and input my new data. So -2, -1, 0, 1, 2, 3, 4, 50, 30, 82, 105, 115, 95, and 45. Okay, so I've got my data. I'm going to input that y1 tilde m x1 plus b. Okay, so looking at the statistics and the parameters that this gives us, I'm going to go over here and I'm going to label that. I'll just label underneath the table what R squared came out as. So R squared came out as 0.120 if I'm rounding to the thousandths. Is that closer to 0 or 1? Still closer to 0. It's a little bit better than number 1, but it is still not great. Okay, so I'm going to make a note. Again, this is not a good fit. Okay, we'll go ahead and write our equation based on the m and the b that they give us, but you can see here, look at our graph. Look at this scatter plot. Again, this line of best fit, it barely touches like one of those points, okay? It is not a very good representation, okay, of this data. So what that means is this is probably not a linear function. A line probably doesn't represent this data best. Some other type of function might, or there just may be no correlation, okay? So what we're looking at, there's the R squared, that's what we're focusing on right now. R is the square root of that number, but R could be positive or negative. The R value is always going to be between -1 and 1. Okay, if it's negative, okay, closer to -1 means there's a strong negative correlation. Your line would have a negative slope. Okay, and if there is a, if it's closer to +1, it's got a strong positive correlation between the two data, the variables between x and y. Okay, and the closer it is to 0, the weaker the correlation. Okay, so not everything can be represented by a linear function. Okay, at least not well. Like we can do this for any set of data, but if that R squared is close to 0, it's really telling us linear is probably not the best fit for this data. Okay, some other function may represent it better, or there just may not be a correlation in the data. Okay, so here when I go to write this equation, M is 5.289 if I'm rounding, X plus, and then my B is 69.286. Oh, hang on. Y'all didn't call me out. Call me out when I make mistakes. I rounded this wrong, my M value. That's 5.286. So they're both 0.286. Okay, now they want us to use that equation and predict when X is 10. So again, we're plugging a 10 in here for X. Okay, so I'm going to come over here and calculate that. So we get 122.146. But looking at that R and R squared value here, R is 0.3. That is a weak correlation. So our coefficient of determination here, being so far from 1, tells us this is not a great fit for making predictions. Okay, that's not an accurate prediction probably. Okay, y'all feel okay with the process though, practicing that process from yesterday? Y'all understand that pretty well? All right, let's flip over. Now, sometimes your data will be given in a horizontal table rather than a vertical table. So you have to make sure that you know what's X and what's Y in the scenario. So this time they're giving us actual context of the data. It says that this data represents the study time, and it's in minutes, versus the test score, okay, for the last algebra exam for 6 students. Okay, so study time and test score. So what is the independent variable? What's the X? What number are you inputting to try to predict which? Like, are you inputting the test score to, no, you're trying to predict the test score, right? So study time is X, test score is Y. Okay, so if it's not labeled, you can label it. So this is X and this is Y. Study time is independent of the test score. The study time happens first. Okay, you can study for as long as you want and then you go take the test and we'll see how prepared you are. Okay, so I'm going to input this data. Okay, so the study times go in my X column. And the test scores go in my Y column. Okay, double check that your values are correct. You don't have any typos or anything. Okay, looks good. Okay, now we're going to type in our linear regression. Y1 tilde mx1 plus b. Okay, we're going to get this information. Hey, look at that x, or not x squared, excuse me. Look at that r squared. What does that tell us? Yeah, this r squared is 0.985. That's pretty close to 1, isn't it? Okay, so this is a good, strong correlation. So our coefficient of determination has determined, okay, we use that value, we've determined that this is going to be a good fit. Okay, so if you want to make a side note that this is a good fit, based on that R squared, or really a great fit for data. Okay, so that means the predictions will probably be pretty accurate that using the equation. So our equation, our M value is 0.672. Remember, we're rounding everything to the thousandths on this one. X plus, and then our B is 58.723. Okay, so this linear model, okay, this equation is a good fit for this data. Okay, it's going to make some pretty good predictions. Now it wants us to use that to predict the test score for a student who studies for 1 hour. Now, the study time is in minutes in the table. So I'm not plugging in a 1. What am I plugging in for X? Yeah, they're saying X is 60. So pay attention to your units to see if you need to convert anything. 0.672 times 60 is 58.723. Okay, so I'm going to come over here and I'm going to calculate that. So 99.048, or excuse me, 043. Now, this one we have the context. On the front, we just were given data. We had no context. We didn't know what it represented. But here, we know that this Y is representing a test score. When I'm grading your tests, am I going to write 99.043 on it? What are we going to round to? We're going to round to the nearest integer. Okay, so what would this be? So a 99 is our prediction for the test score for the student who studies for 60 minutes. You'll feel okay about that one? So when you have the context, when you have the scenario, make sure that you round correctly, you use correct units, all that jazz. All right, last one. Okay, now this one gives us in years, it tells us the year. So from 2014 to 2020, we have the data on the time spent on the mobile device in minutes. Okay, and it says in the question, it says this is the average time people spend on their mobile device per day. Okay, this is data taken over a 7-year period. Okay, so this is the average daily minutes spent on their phone, on their cell or their mobile device. Okay, in this year through 2020, so 2014 to 2020. Okay, for adults 18 plus. Okay, now when I go to enter this data in the table, y'all may remember we had a question yesterday in our notes where our X column represented years since the data started being collected. Okay, we didn't actually plug in 2014 for X, okay, or whatever the year was. We plugged in how many years since the beginning of the data collection. Y'all remember that yesterday? So we're going to do the same thing here. So I am not going to use the year as my X. I'm going to have my X be the years since 2014. Because 2014 is the first year we have the data. So years since 2014. So in 2014, how many years since 2014 has it been? 0. That's 0. That's representing my y-intercept, isn't it? Okay, and so then I'll just count here. So now that's what I'm going to enter for my X column, and then the minutes in my Y column. Bless you. All right, so let me enter my table. Zero. All the way to 6. All right, so 152, 169, 188, 205. Oh, it's going up every year. 215. Oh, we stayed the same that year, a little stagnant. And then 229. All right, so now I'm going to do y1 tilde mx1 plus b. Okay, take a look at that r squared. What does that tell you? Yeah, if I'm rounding the thousands, that's 0.947. Is that a good, strong correlation of determination, or is that like not a good fit? It's a good fit. It's closer to 1. Okay, 0.9 is a good correlation. Okay, so this is going to be a good fit. Okay, this model that we come up with is going to be a good fit for this data. That means it's going to make pretty accurate predictions. Okay, so my equation, M is 12.5. B is 158.643. Now y'all go ahead and try to figure out what are you plugging in for X for that prediction in 2030. So let's, sorry for that interruption. All right, what did y'all come up with for, what does it mean? What do they want you to plug in for the year 2030? If X is the years since 2014, what is 2030? 16. Okay, look at where the table stops. The table stops in 2020, and that's been 6 years. So 2030 is 10 years after that. So 10 plus 6, that's 16. So they want us to plug in a 16 for X. Okay, so when I do that, I'm going to come over here and I'm going to put 12.5 times 16 plus 158.643. And so my prediction is 358.643. But again, we're talking about, this is representing minutes. So I don't want this decimal. So that is going to round to the nearest whole number, is going to be approximately 359 minutes. Good? All right, so you've got some linear regression, mixed practice. Some is creating the equations using the Desmos process. Some is making a lot of making predictions questions, and then some of the interpretation, like we talked about yesterday, interpreting what does the y-intercept mean in this problem. Okay, so you've got a delta math. With today's date, it says linear regression day 2 or part 2. Okay, and that's what you should be working on. Unless you're behind on something, you're welcome to work on a past delta math if you need to, or you're working on today's practice.